Okay, great. Everybody can hear me loud. So I'm going to give a history of Bayesian neural networks. And I wanted to dedicate this talk to my friend and colleague David Mackay, who's probably the smartest person I've ever met, who sadly died this year and was a pioneer of this field. And I'm really delighted that Ryan Adams has a tribute to David talking about his contributions to the field, which were incredible and numerous. Okay, so I'm apparently a NIPS old-timer now, so that means I give talks about history. And I have 30 minutes to talk about 30 years, so I'm going to go pretty quickly. All right, so let's go and dive into it. So 30 years ago, as I said, back in the 1980s, there was a huge wave of excitement in neural networks. It was amazing. I was a teenager at the time, and I was already, interested in this field. And, Boltzmann machines came out in 1985. The backprop paper that appeared in Nature came out in 86. And these lovely PDP volumes came out in 1987. Who remembers or knows the PDP volumes? How sad. These were classics. This is like what launched the field in the 1980s, and you could go back in there and find a lot of brilliant ideas. Unfortunately, if you search for deep learning, you won't find this stuff because it used to be called connectionism. And NIPS was this main conference, which launched in 1987. And sort of like at that time, I was an undergraduate, and I worked on recurrent neural nets for natural language parsing, which seemed like an amazing and crazy idea. Of course, it didn't work because we had hardly any data and hardly any compute power. So that was the 1980s. Well, the talk is about Bayesian neural networks. I just want to set some standard terminology clear. I probably don't need to describe what a neural network is, but I'm going to do it anyway because I'm going to do it my way. A neural network is a parameterized function. So like any machine learning problem, you have some data. Let's take x's and y's. By neural network, I mean kind of a multi-layer perceptron and variations of it, feed-forward neural networks. Of course, we could talk about other versions. Any parameterized function has parameters. Let's call them theta. The parameters correspond to the weights and biases in the neural network. And a feed-forward neural network models a distribution over some outputs given some inputs and theta. And generally, it's a nonlinear function of both theta, the parameters, and x, the inputs. So this is, for example, for a binary classification neural network. This would be called logistic regression as well. It's some linear combination of inputs with the weights passed through some nonlinearity like the logistic, or it could be probit or something like that. Okay, of course you can vary all these things. You can vary the nonlinearities and make them ReLUs or whatever you want, and you can stack these functions together. So multi-layer or deep neural networks are just models of some overall function that are expressed in terms of compositions of functions. Like, for example, here, this would be called a two-layer network. And usually what people do is they train these networks to maximize some likelihood or some penalized likelihood, which you can call an error function if you don't like the word likelihood. And they tend to use variance of stochastic gradient descent to do that. So that's a neural network. Well, let's just fast track to the present for a minute. What's deep learning? Well, deep learning is basically, it's a lot of things, but to one slide approximation, deep learning systems are neural network models similar to the ones that we had in the 80s and 90s, with a few important differences. One of them is that we've had some good ideas since the 80s. We've had some architectural and algorithmic innovations, things like having many layers, using ReLUs, better initialization and learning rates, dropout, LSTMs, et cetera, et cetera. The list gets longer every time you look at arXiv. We also have, importantly, vastly larger data sets, web-scale data, which we didn't have back then. We have vastly greater compute power, including GPUs on the cloud and so on. We have much, much better software for dealing with this stuff. which is great and generally open, and there's a huge amount of investment and media hype. So that's the difference between now and the 1980s. Okay, so the talk is the history of Bayesian neural networks. I've talked about neural networks and a little bit about deep learning. Let's step back a little bit and think, well, what are the limitations of deep learning? Is it the panacea that's going to solve everything in life? Well, neural networks and deep learning methods are amazing. They give great results on many benchmark tasks, but they generally are very data hungry. Often they need millions of examples for things, very compute intensive to train and deploy, poor at representing uncertainty, something I'll come back to in a few minutes, easily fooled by adversarial examples, finicky to optimize, you require a lot of expertise and so on, and generally uninterpretable black boxes lacking in transparency and difficult to trust. I love them. They're great. But we have to acknowledge that there are a lot of issues, and fortunately, every one of these bullet points here, there are people at this conference working on. So I'm not saying that nobody's working on these things. We're all working on these things. Okay, so the talk is about, and the whole workshop is about Bayesian deep learning. So what do I mean by being Bayesian, okay? So let's be clear, neural networks have parameters. When we talk about Bayesian neural networks, we talk about dealing with all sources of parameter uncertainty, okay? For the parameters are uncertain, given the data, and also potentially dealing with the structure uncertainty, maybe, you know, how many hidden units, how many layers, etc. Okay? So, yeah, parameters are the weights, and structure is the choice of architecture, number of hidden units, choice of activation functions, etc. That's what Bayesian means. I'll go into this in a couple slides of tutorial, just in case. So Bayes' rule is just a way of updating our beliefs about hypotheses given data. It says that before we observe data, we should express our knowledge or state of knowledge about hypotheses through a probability distribution. That's the best way to represent uncertainty. Before we have data, we should better have some uncertainty, so let's represent it. That's called a prior. And then any hypothesis can be evaluated by scoring the probability that it gives to the data under that hypothesis. That's called the likelihood. And Bayes' rule, which comes from the basic rules of probability theory, says the way you combine the prior and the likelihood is you multiply them and you renormalize over the space of plausible hypotheses you're considering. And that's learning from data. And when I'm talking about hypotheses, I mean anything that's uncertain. And when I'm talking about data, I mean only the measured things. And in machine learning, the only thing that's measured is the data. Everything else is uncertain, the parameters, the structure of the model, and so on. So Bayesian method tries to be honest about the fact that we have uncertainty about all of these things. This is my obligatory one slide on Bayesian machine learning as backup. So essentially, even Bayes' rule is not a, is not a principle. It's a corollary of two more fundamental rules, the sum rule and the product rule of probability. Everything follows from the sum rule and product rule. And if instead of x's and y's, we write it in terms of the symbols that we care about, like theta for parameters of a model, m for a model class, d for the data we might observe, then we get learning as just one simple expression, which is apply Bayes' rule to your state of knowledge, which was the prior, once you observe the data, and then you get your posterior state of knowledge, which is the posterior of a parameters given data, and that's your prior for the next bit of data that you observe. There's nothing really different between a prior and posterior, okay? It's just states of uncertainty. If you want to make predictions, the sum and product rule tell you that you should be taking the predictions for every parameter value and averaging those predictions with respect to the posterior probability of the parameters given the data. So Bayesian prediction is naturally an ensembling method. If you want to compare models, you don't have to come up with any new principles. You just apply the Bayes rule at the level of model classes, which we get here. Okay, so that's Bayesian machine learning in one slide. It's incredibly theoretically straightforward. It's hard to pick holes in it unless you don't like priors. We can talk about that later on if you want. Okay, so why should we care? All right? Well, we should care because we should care about having calibrated model and prediction uncertainty. If we're going to deploy these things in the real world, they better know when they don't know. And they better be able to tell us when they don't know, because if decisions are going to be based on the outputs of our machine learning methods, if they're overconfident, we're going to have big problems on our hands. That's one of the reasons we should care. Calibrated uncertainties. Of course, there's a lot more to machine learning than calibrated uncertainties, but we'll get to that in a minute. The other reason I find very appealing is that this framework, these equations on the previous slide, give you an automatic way of capturing model complexity control and doing structure learning. So, you know, if you're trying to search over a space of possible models for a good model for the data, and you want to compare models that are very different from each other and so on, then Bayesian Occam's razor, which is just, it just follows from these basic rules, tells you a way of doing that. Here's a very nice figure from Yaron Gal's thesis, which just has just been submitted, called Uncertainty in Deep Learning. This is a nice figure to represent what prediction uncertainty might look like. So I have some data, I'm learning some function. Remember, neural nets are just the ways of learning functions. Where I have the data, I know what the function looks like. Where I don't have data, I better have a good representation of my uncertainty. And that's what this shows that you can do. I also wanted to thank Yaron because he dug up some very interesting papers I didn't even know about in the history of neural nets. Okay, so that's why we should care. And I want to make a simple note about models versus algorithms. Historically, actually, NIPS used to have tracks, but they weren't like parallel tracks. They were just tracks that you submitted to. And the biggest track by far was always the algorithms and architectures track. And I like the term algorithms and architectures because it separates, I would call it models versus architectures. So models are things that I've listed here, just some random examples of models: ConvNets, latent Dirichlet allocation, recurrent neural nets, HMMs, Wilson machines. These are models. These are representations of data. And we better really cleanly separate models from algorithms, which are examples of algorithms like SGD, conjugate gradients, MCMC, et cetera, are listed in this column here. And algorithms are things that target some kind of learning, either finding some optimal parameters, theta star, like maximum likelihood or map algorithms, or they might target finding the posterior distribution, the probability of parameters given the data, like MCMC, variational Bayes, et cetera. And the important thing to remember is that often these algorithms are not so different from each other. The ones that do optimization and inferring posteriors are not all that different. And also that Bayesian belongs firmly in the algorithms category. I can be Bayesian about any of these things I want. Give me, in fact, any well-defined model, and you can treat it in a Bayesian manner. Okay? That well-defined means that it has to give probabilities to data in some way, and all neural nets do that, basically. Okay, so models versus algorithms, you could mix and match these as you please. All right, so now I've defined Bayesian, I've defined neural network. What's a Bayesian neural network? It should be pretty obvious right now. Here is a neural network. It's a representation of functions with some parameters we call theta, which are the weights of the neural net. And then a Bayesian neural network just means treating those parameters in a Bayesian manner. So before you observe the data, you have a prior over the parameters, which might have some what are called hyperparameters, controlling things like the width of the prior. That represents sensible ranges of weights that you're willing to consider for your data. Okay? It's a soft way of representing ranges, is the way I like to think about it. Then once you observe the data, you get the posterior through some algorithm. And then if you want to make predictions, it's a little bit more expensive. You don't choose a single parameter value. You're supposed to average over parameter values to make your predictions in some approximate way. Okay, that's all a Bayesian neural network is. And now let's talk about the history, where it starts getting fun. And this stuff does literally go back well, 29 years, okay, at least. So here is a lovely paper by Denker et al. With lots of great authors here, people like Sarah Soya and John Hopfield are on there as well, which is called Large Automatic Learning, Rule Extraction and Generalization in a journal called Complex Systems. And if you look at this paper carefully, basically it talks about choosing probability distributions over weights of basically what's a neural network. And then I love this sentence: we can map the weight space onto function space as follows. So, you know, people have done that. You know, you can think about the representation of functions, distribution of functions represented by a neural network, which is a more intuitive thing to think about than the distribution of weights, which is kind of an arbitrary nuisance parameter usually. And then basically it talks about integrating over weight space and so on and so forth. An interesting early paper. It's not exactly doing the stuff that we now call Bayesian neural nets, but it definitely talks about this stuff. 87. Okay, now we move on to 89. Note the affiliations. A lot of this stuff was going out at AT&T, and John Hopfield was also at Caltech. Again, I think kind of an AT&T heavy group. Here's a paper from 89, Consistent Inference of Probabilities in Layered Networks, Predictions and Generalizations. And here we have it. There it is. Bayes' rule applied for neural nets. And then if you look at section 4, here is an interesting application of what they do. They say to demonstrate the utility of the average prediction error for determining a sufficient size of the training set as well as selecting the optimal architecture of the network. Okay, so 1989, they were using Bayesian inference to try to figure out optimal architectures of neural networks. Denker and this other guy, who you might have heard of, Jan LeCun. Next time you see Jan, are you on video? Yeah. Jan, I didn't know you were Bayesian. He'll like that. Well, you know, Jan has a classic paper on Bayesian inference with John Denker, who was the first author of this paper, where essentially the contribution of this paper is to try to algorithmically figure out how to compute this posterior over the parameters. And the way they do it is they optimize the parameters and they compute the second derivative of the likelihood with respect to the parameters, the log likelihood with respect to the parameters, which is the Hessian. The diagonal versions, the diagonal elements of the Hessian are these HIIs. And then that's an estimate of the posterior. And that's called Laplace's approximation. That's a diagonal version of Laplace's approximation for neural nets. And also in 1999, there was a very lovely paper by Ray Buntin and Andreas Weigand, which is also doing very clearly expressed Bayesian inference on neural networks. Okay, so now we're entering the golden era of Bayesian neural networks. Around 1992, a whole series of papers that David Mackay wrote coming out of his thesis. And this one is one of the most beautiful ones. It's called the Practical Bayesian Framework for Backpropagation Networks. So he's really taking this stuff and trying to make it very practical. And I think the abstract itself is lovely to read. Quantitative and practical Bayesian framework is described for learning of mappings in feed-forward networks. The framework makes possible, 1, objective comparisons between solutions using alternative network architecture, so architecture selection. 2, objective stopping rules for network pruning and growing procedures. 3, objective choice of magnitude and type of weight decay terms or additive regularizers. So all that regularization ad hocery, you know, is sort of subsumed by thinking about the Bayesian framework. 4, a measure of the effective number of well-determined parameters. 5, quantified estimates of error bars on network parameters and on network output. So prediction errors, as I showed you from Yarin's figure. 6, objective comparisons to alternative learning methods, and so on and so forth, like splines and radial basis functions and so on. Beautiful paper. If after today you want to go read one paper, maybe this should be the one. All right. So then now things were getting serious, 1992, and so now this is NIPS 1992, my first NIPS, and the proceedings came out in 1993. Okay, so December NIPS 1992, the papers came out in 1993. Here is a paper by Radford Neal in NIPS 1993 called Bayesian Learning via Stochastic Dynamics. Again, you know, an absolutely beautiful, brilliant paper. So what does this paper do? Well, this paper is the first MCMC, Markov Chain Monte Carlo sampling algorithm for Bayesian neural networks. So David Mackay did a Laplace approximation very elegantly, and Radford Neal at around the same time was doing Markov Chain Monte Carlo. And in fact, he didn't do any kind of old Markov Chain Monte Carlo. He did something very sophisticated. He used what he called hybrid Monte Carlo, what we now call Hamiltonian Monte Carlo, HMC, which is a sophisticated Markov Chain Monte Carlo method that uses gradients to sample efficiently. So here is how this stuff works. You have a neural network. You do backprop on the neural net. That's what gives you the gradients. And now instead of just optimizing with those gradients, you follow those gradients in some way according to the HMC algorithm, and occasionally you reject moves given by those gradient computations to sample from the weights. Amazing, elegant paper. So he was writing his thesis at the time. This is his cover page of his thesis, 1995. Along with doing hybrid Monte Carlo for Bayesian neural networks, the thesis also establishes a link between Bayesian neural networks and Gaussian processes, which the machine learning community basically didn't know about, and so he introduced Gaussian processes as a way of thinking about simplifying Bayesian neural networks into the community. And he also describes automatic relevance determination. I'm going to spend a couple of slides describing what these things are because they're useful concepts. Gaussian processes are a way of representing unknown functions. So imagine you're doing a function approximation from x to y, and you want to learn that function from some data, like these magenta dots. And instead of fitting a function with some parameters, we're going to be what's called non-parametric. We're going to consider a probability distribution over the space of functions. And that's our choice is going to be a Gaussian process that defines a distribution over the space of functions. And then we can apply Bayes' rule, sort of loosely written here, over the space of functions in the following way. And a Gaussian process is just an infinite dimensional generalization of a Gaussian distribution. And we can use Gaussian processes for any kind of regression, classification, ranking, dimensionality reduction, et cetera task. In fact, any task for which you have an unknown function. So this is what Gaussian processes are. And what was the, let's just describe some of the relationships. As you all, or many of you know, I like drawing these cubes. So you can start with, here's one way of thinking about Gaussian processes. You can start with linear regression, and you can apply various operations to linear regression to get other models. For example, you can kernelize linear regression. Kernelizing means map your features into some high-dimensional feature space and do the linear task in the high-dimensional feature space. So these are the orange arrows, kernelizing. The blue arrows are take a model and treat it in a Bayesian manner. So remember, any model can be treated in a Bayesian manner. That just means do inference over the distribution of parameters instead of just fitting of the distribution of parameters. The magenta arrows are take a regression model and turn it into a classification model by assuming a different type of output, discrete output instead of continuous outputs. So you have linear regression, you have Bayesian linear regression, and kernelized Bayesian linear regression is Gaussian process regression. Support vector machines lie here. They're kernelized linear classification, essentially. And Gaussian process classification is sort of the Bayesian analog of support vector machine classification. Okay? So here's how Gaussian processes are related to logistic regression, linear regression, SVMs, et cetera. How are they related to neural networks? Well, this is what Radford Neal determined in 1994. He basically showed that if you have a neural network with one hidden layer, and people were worrying, how do I choose my number of hidden units? People seem to still worry about that. Well, he said, if we take the infinite limit of having infinitely many hidden units in that one hidden layer, and we treat the neural network in a Bayesian manner, so we give Gaussian priors, we could give other priors, as long as they're independent, But Gaussian is an easy case. If we give Gaussian priors to the weights, and we scale the widths of those Gaussians in a way that we can take this limit sensibly, then this is exactly a Gaussian process, okay? And different choices of the nonlinearity give you different kernels, okay? So there's like, you know, the neural net kernel, there's sort of a kernel corresponding to ReLUs, there's a kernel corresponding to all of these different things. Radford also went on to talk about like limitations of Gaussian processes. Again, his thesis is beautiful to read. He talked about things like, well, what would happen if you had deep networks, or maybe even infinite? He even talks about infinitely deep neural networks and so on. Okay. Another thing I said Radford introduced in his thesis, which was actually joint work with David Mackay, is this idea of automatic relevance determination, or ARD. So if we have a Bayesian neural network, we might want to do something called feature selection, where we might want to say which of the input features are relevant and which ones are irrelevant. And let's try to do that automatically. That's what automatic relevance determination does. And the way ARD works is that you take the weights of a neural network, and then you say there is a hyperparameter alpha d corresponding to the outgoing weights for each of my input units, little d, okay? So when alpha d, what alpha d is the precision of the Gaussian, the inverse width of the Gaussian in the prior, okay? And now we do a thought experiment. So let's do the following thought experiment. If alpha d goes to infinity, well, what's that? The precision of a Gaussian goes to infinity, means the variance of the Gaussian goes to 0. If you have the prior on the weights saying 0 mean and 0 variance, that means that all of those outgoing weights get zeroed out. Okay, they disappear. So that means that input d is irrelevant. On the other hand, if alpha d is some small finite and not infinite number, then you have some finite variance, then the weights coming out of input d can vary, so feature d is relevant. And now the cleverness here is that if you do Bayesian inference over the weights, then you can actually optimize the alphas. This is sometimes called type 2 maximum likelihood or level 2 maximum likelihood. You can optimize the alphas, and what that will do is it will optimize something that figures out from the data which inputs are relevant and which inputs are irrelevant. And now you can actually apply that reasoning at every layer of your network. So it doesn't have to be just at the input layer. You can apply that at every layer of your neural network and get the system to automatically cancel out the roles of individual hidden units and make them disappear from your network. So this is a way of doing feature and architecture selection from a Bayesian framework in neural networks. And interestingly, this idea got ported over to Gaussian processes, so people in the GP community now know about automatic relevance determination, but it came out of neural networks. Okay, so what about variational learning? So we've talked about Laplace approximations, which are these Gaussian quadratic things. We've talked about MCMC, which Radford Neal introduced. Well, what about variational Bayesian learning of neural networks? Where would you go to find the earliest reference to that? So here we have a paper that if you read it, it doesn't use the words variational, or I don't think it maybe even talks about KL divergences. I'm not sure. Maybe it does. This is a paper in Colt 1993 called Keeping the Neural Network Simple by Minimizing the Description Length of the Weights. And essentially, in modern language, what this is called, what this actually does is it derives a diagonal Gaussian variational approximation to the Bayesian neural network weights, but it's just couched in an information theory MDL language. Because the beauty, by the way, of Bayesian methods is you could talk about Bayesian methods from minimum description length, from information theory perspective, et cetera, and it's all equivalent. Okay. Then this idea was generalized in '98. I'm jumping forward a little bit. By Barber and Bishop, which in this case, they called it ensemble learning in Bayesian neural networks, because ensemble learning is another synonym for variational approximations that you might want to look up. This paper does full covariance Gaussian variational approximations to the Bayesian neural network. I'm being told to accelerate. Here is the abstract of the Hinton and Van Camp paper. You read it. It doesn't sound like it's doing variational inference, but that's what it is. Read it carefully. The target, remember, the target of Bayesian inference is a posterior over weights. MCMC takes a chain of samples such that those samples converge to the distribution, P of theta given D. Variational Bayes finds an approximation Q of theta that is the argument of KL Q of theta to the posterior. Okay, just as a reminder. All right, here's an interesting aside. It's a really important aside. Right around the same time, in 1991, Radford Neal wrote this other paper called Connectionist Learning of Belief Networks. And what this paper does is it explicitly links feed-forward neural networks, which were also called connectionist networks, and graphical models, belief networks in this case. And in fact, what it does is it says if you have a feed-forward neural network with sigmoid activation functions, instead of thinking of those units as deterministic, let's think of them as binary random variables. That thing is called a sigmoid belief network, and you can do learning in that by Gibbs sampling. Again, incredibly beautiful, very nice, and definitely worth knowing about. And, you know, for example, we've extended on this line of work by having a Bayesian non-parametric version of this model, which samples over the number of hidden units, the number of layers, and type of hidden units in these types of belief networks. And in fact, in this paper, we're trying to learn the structure of infinitely wide and infinitely deep belief networks. So here's another cube. If you're looking at probabilistic models that, probabilistic generative models, some things that, you know, people might know here in terms of VAEs and so on, you should probably start with factor analysis, which is over 100 years old, and then think about different operations you could do to that, make undirected versions or deep versions. Again, a synonym for deep, if you go back a few years, is hierarchical. There are a whole bunch of papers that talk about hierarchical generative models. In fact, I have a paper, for example, with Jeff Hinton, where he talks about rectified Gaussian belief networks, which are hierarchical generative models with rectified Gaussians. Nowadays, that same paper would probably be called deep ReLU networks or something like that, because that's exactly what it was. And then you can have deep Boltzmann machines, et cetera, et cetera. I probably should accelerate. But deep and hierarchical, synonymous. Okay. We're coming closer to the present. I wanted to highlight, I've skipped over many papers. I apologize to lots of people who've done great work. I'll mention some at the end. I wanted to highlight a particular paper by Max Welling and Yi-Wei Tai called Bayesian Learning via Stochastic Gradient Langevin Dynamics. And it combines SGD, as we all know and love, with Langevin dynamics, a form of MCMC that Radford Neal introduced the machine learning community to get a highly scalable approximate MCMC algorithm based on mini-batch SGD. And I just want you to look at equation 4 of this paper, because what is it? Well, it's an update rule for your weights, which says take the derivative of the log likelihood of your mini-batch with the log prior. This is just SGD with some learning rate epsilon. And what are you going to do to that SGD? Oh, you add some noise. You add some Gaussian noise to SGD. Oh, that's just like, that's not even a line change in your code. That's a few characters change in your code, in your SGD code. Okay? A few characters change in your SGD code turns your SGD code into an approximate MCMC algorithm that does Bayesian inference. Okay? That's what I mean by, you know, optimization and Bayesian inference don't have to be that different. Okay. There are a whole bunch of papers that have come out in this sort of revival of Bayesian neural networks, a lot of great stuff over the last few years. There's a lot of fun we're all having, and I'm glad to see that there are lots of people in this workshop as well. It's hard to call it a workshop when it's in a room this big. So I'm going to wrap up by reminding people, well, why do we need probabilities? Okay. So I think the probabilistic modeling approach is essential for a lot of problems in learning and intelligence, where essentially we need to carefully represent uncertainty. So these are problems like forecasting, decision-making, learning from limited, noisy, and missing data, learning complex personalized models. All of data compression is probabilistic modeling. You know, I think automatic model discovery, scientific modeling, experiment design, active learning, etc. All of these are fundamentally reliant on estimates of probabilities. Okay, so I don't think probabilities are going anywhere. They're here to stay with us. So I'm going to conclude. Probabilistic modeling offers a general framework for building systems that learn from data. Advantages include better estimates of uncertainty, automatic ways of doing learning of the structure and avoiding overfitting, and a very nice foundation. The disadvantages include higher computational and memory cost, but it depends on your approximate inference algorithm. You know, you can write down your probabilistic framework and then say, okay, I'm going to approximate it away until I get something that is about as fast as running SGD on my neural network, when we have approximations like that already. And Bayesian neural nets have a long history, and they're undergoing a tremendous wave of revival, so it's quite exciting. So this paper I have at the bottom is not about Bayesian neural nets. It's just an overview of probabilistic machine learning with some some of these arguments spelled out in some interesting directions. Okay, so that's it. Happy to take questions if we have time.
Thanks for the great talk, Zoubin. And thanks also for mentioning the importance of David in inspiring a lot of the work in this area. So I'm also a great proponent of the separation of the model and the algorithm. But since this is a small workshop, I think we can have a lively philosophical debate. I'd like to take issue with your firm placement of Bayesian inference in the algorithm side. As I think you would agree, or in fact, I'm actually quoting you. So Bayesian inference is just the calculus of uncertainty. And in that sense, it's far more fundamental than either a model or an algorithm. It's like mathematics. It imbues everything. So I think it's sort of cheapening it to associate it firmly with the algorithm.
Yeah, you're right. You're right. It's, thanks for, correcting me by quoting me. You're right. In the sense, Bayesian inference isn't an algorithm any more than calculus is an algorithm. Okay, calculus is the language, the mathematical language of rates of change, you could say, and probability theory is the mathematical language of uncertainty. And so Bayesian methods are methods that try to adhere to the rules of probability theory. But there are a whole bunch of algorithms that are subsumed by that. Yeah, thanks, Neil. Hi, Matthias.
So thanks again, wonderful talk. I noticed at the beginning of your talk you mentioned two reasons why deep learning took off so much, and there were availability of huge number of computations and amazing software. I'm just wondering whether you can comment on, whether the Bayesian crowd is taking advantage of that and what we can expect in that direction.
That's a great question. I think the Bayesian crowd has not taken advantage as much as it could have in those things. There's good software for Gaussian processes, for example, but not sort of an industry strength, let's say. Although there are recent efforts, like for example, we've recently implemented Gaussian processes in TensorFlow, for example. So now, any advances in TensorFlow on the software or hardware side, you can use Gaussian processes for that. The other area that I think is very interesting, that I'm certainly excited in, is probabilistic programming, where the framework there should be to abstract away the inference algorithm so that people can get around to writing down their model. Just like in the deep learning community, people basically wire up their deep learning architecture and then just call an optimizer to learn on that. And that just makes their life easier because they don't have to rederive things. So we can do the same thing in probabilistic modeling by doing probabilistic programming, and we can interface all those, sort of computation graphs, automatic differentiation, all of that can be used for probabilistic modeling as well.
Can I follow up on that? This is a shameless plug for
Oh,
the
yeah.
Edwards system, developed by David Bly's lab, and we at Google are collaborating with them. So it's open source, it builds on top of TensorFlow and Theano, and it implements almost every algorithm you just heard, and it's highly scalable. Edward?
Edward.
Edward.org.
It's good stuff. Yeah.